apologize ahead. My throat is in not pristine conditions. I hope I would be able to go through these lectures. And in the previous lecture, we solved a particle in a harmonic potential. We used for it a specifically constructed pair of operators, creation and annihilation, and we saw that it's extremely convenient for expressing the eigenfunctions and eigenvalues of the harmonic oscillator. Okay, what we are going to do today is actually, hopefully, two things. One is just fleshing out a few things about the harmonic oscillator. Mainly, we used there the Hermite polynomials, and I want to connect it to the general knowledge of Hermite polynomials. And the second thing is to solve a wave packet in such a potential, which basically is in some sense summing up of a lot of things that we did until now. And the second part of the lecture actually will move to our space, three-dimensional. Until now we were mainly in one dimension, and start the procedure of studying about angular momentum, which is a very important concept in physics in general and in the solution of particles in symmetric potentials 3D, which will eventually lead us to the solution of the hydrogen atom, which is like the cornerstone of the first years of quantum mechanics. Okay, so in the previous lecture we wrote down a definition. And in order to calculate, explicitly write down the Hermite polynomial for any n, basically we have here an algorithm. Go, perform the derivative n times. You'll remain with e to the minus y squared. It will be cancelled out by e to the y squared, and you'll be left with a polynomial. Straightforward, simple. And we can go and perform it. For the first few polynomials. Okay, what are the properties of these polynomials? Well, first of all, they come out from solving a differential equation that Hermite solved a couple of 100 years ago. So this is a differential equation, the one that emits solved, and the least polynomials solved. Okay. We could have actually got to this point in solving the Schrödinger equation by assuming that our solution looks like e to the minus x squared times something, and this something would have been the polynomial. So that would have been the straightforward way to solve it without using creation and annihilation operators. Now, physics, why should it die out like a Gaussian? Just because of this, it clearly has to die out. You would have tried an exponential and it wouldn't work. It needs to be something stronger, so it's a Gaussian. Okay, so what are the properties of these? Actually, I don't want to write it here. First of all, it's a solution of this equation. 2, trivially, it's a polynomial. Of order n. Okay, if this would have been a course on mathematics, I would have to prove the first one I actually proved from the definition here. The other two I should have proved, but there's no need because we have already learned it. We have learned that any one solution for a one-dimensional potential which has discrete energies cuts the wave function cuts the zero n times. That's exactly what's written here. The third part has a definite parity. Of course, the potential has a definite parity. And as we have shown in one of the previous lectures, it forces us that also the wave function will have a definite parity. So we know all of these properties, basically from knowing that this is a solution of a harmonic oscillator. So what do I mean by orthogonal under a measure, or orthogonal if I put the right Jacobi weight? Basically, this is the weight, and this is orthogonality. It's not orthonormality. If I would divide it by it, it would be orthonormal. From where do we know it? Do we have to solve it? No. If n and m are eigenvectors of the Schrödinger equation, they must be orthogonal. Proof. So I can use something that I can give it a name, the Hermite transform, to describe any function that behaves in this way. Okay, how do I prove that it works for any function? I don't need to. Any function which is a kosher wave function, meaning I can normalize it, I can write down as a sum over the basis function. Finish. So if someone asks you, prove that any function can be written as a Fourier transform, no problem. The basis of a free particle are the e to the power I kx. I can write any normalizable function as a sum of these guys. I finished my proof. So I'll give another two properties. One of them is very useful. Let's say for writing a simple two-line computer code to calculate any order of the Hermite polynomial, or even with a pencil and pen, it's doable, and that's recursion relations. So the first one requires only knowledge of the previous Hermite polynomial. Unfortunately, it gives you only the derivative, so you have to know how to perform an integration. It's not so terrible because these are polynomials. We're supposed to be able to perform an integration on x to the power some power. And the second one is completely straightforward, but you need two possibilities. Okay, check at home if it works for the three that I gave you. Is that 5? 6 is of interest to perhaps the more mathematical inclined setting here, if there is none. So I just write it down. You know, and that's generating function. I do want you to at least once hear about the concept of a generating function. So, what is a generating function? It's a function of two variables, s and x, that if I write it down as a series, I get it as powers in S times the Hermitian polynomial. And that's called, for any function, this is a generating function of this function. In this case, I'm looking for the generating function of the Hermite polynomial. Okay, let me just write it down and see that it's true, that I have such a function, and the function that I've written down is indeed the one that I'm looking for. Okay, someone has an idea. How will I show that this is indeed the generating function of the Hermite polynomial? To bring it to this form, what does it remind you? Taylor expansion. Once someone gave me this, all I have to do is perform a Taylor expansion of this function and see that it corresponds here to the value. So I just explicitly have written the Taylor expansion. Nothing more. But the definition which I started the lecture with, so it's a generating function. Okay, so that was a mathematical interlude. Good. So, to conclude with the harmonic potential at the moment,
one to n. It's part of the portion of I'm thinking.
No, it's part of the expansion. I forgot to write it down, and I was too lazy to bring a black. Okay, so I want to see the development of a wave packet as function of time in a harmonic potential. Okay, what actually do I want? I want to have a wave packet at time t0, which is a wave function. And I want to get its behavior at time t. So I have two different ways to do it. One is to feed it into the Schrödinger equation, put the boundary condition and the initial condition, and move on. The other way is, which we have at least discussed a few times, let's assume that I can write it down as a superposition of the eigen vectors of the potential, of the harmonic potential. Why can I do it? If I'm a physicist, then I will answer it's a basis and therefore can describe any function. If I'm a mathematician, I've learned that for the Hermite polynomials can describe any function that is normalizable as a sum of these Hermitian polynomials. Okay, most of them are valid answers, but I can do this, and I know since the potential is not time dependent. What's more, I know the value of the energies. So what remains open? What are the amplitudes of this expansion for a given wave function? Okay, there basically I have the general answer, which is always true. The scalar multiplication this is always correct. So, the two mathematical problems that I'll have here, one is to perform the scalar multiplication. It's not necessarily a nice integral. And the second, performing the summation. Not necessarily an easy summation, but we'll make life a bit more easy by that if we'll take a Gaussian as the initial condition. In that case, life will be somewhat easy. So, in general, so I started by placing a Gaussian with some width, which I didn't define, so it's A0. Centered around x0, it's not necessarily in the middle of the potential. At the moment it can be anywhere. Because I prefer to work here in dimensionless variables, write down y is x a0 and y0 is x0 over a0 and psi of y and 0. So till now, except for massaging the a wave function. I didn't do basically. Now I can go and perform the integration. Because I remember that something about the definition of the Hermite polynomials has to do with Gaussians times these polynomials, and I've seen something about the generating function that has also some x minus s square property. So I stop a moment and say I can pull out here all bn's much more easily than going and performing this integration. You see that we have here a recurring theme that we're trying to avoid to do ugly mathematics. Okay. And I forgot the normalization. Okay, so what did I do here? Really nothing. I just opened up the parentheses and wrote it down in a strange way of y, the first y squared over 2. Second one I broke to two parts. So y0 squared over 2. And the last term is just the multiplication between them. See it? Give you a couple more minutes. Look on the similarity between this and the generating function. And exchanger x with y0 over 2. And once we convinced ourselves in this connection, we are finished. If you don't see it at the moment, take 5 minutes at home and look at it more carefully. Okay, all I have here is a constant, and I can write down Bn as so instead of performing a lot of integrals, an infinite number of integrals really, I got here the development in time. Oh, sorry, I got here the amplitudes of the expansion of the Gaussian as function of eigenvectors of the energy easily. Okay, so I have this guy, I have this guy. All I have to do, is to sum it up. Okay, let's go and do that. So, here. So what did I do here? Nothing beyond writing down Bn explicitly. and entering the explicit value of the energy. And since half times h bar omega is a constant, so I pulled it out before the solution. Okay, doesn't look like a summation that I'll have fun doing. Let me simplify it a bit. I'm allowed to do it. Let me write a shorthand of what's written in the parentheses. Okay. This is exactly the same summation that I had in the beginning. But instead of y0 or x0, in the original case I have here y0 multiplied by some function of time. So for clarity, I'll write it down in the following form. Some time-dependent constant, and in a moment I'll define it. And the important thing is this is a beautiful answer. What does it tell me? I still get a Gaussian. Now, the position of y0 depends on t. And in order to handle the normalization, I'll have here a normalization factor that depends on time. But the main feature, a Gaussian, that moves exactly like a classical particle in the potential remains. This is a very unusual situation, but cute. Has nice mathematics and also a nice solution. Okay, so I'll just write down Okay, now if someone here has a keen eye to details, she or he should have stopped me and said, 1 minute, you're a bit too loose. Why? Because Y0 that I'm selling to you is actually the position, right? But this has an imaginary part, right? Because, so why are you telling me that the center of the Gaussian moves like a classical particle, but here it has some imaginary part? So the answer would be, yes, you're right. I had to treat it a bit more carefully. And the reason for it is that a wave function doesn't give me the position of the particle. The wave function squared gives me the position of the particle. And therefore, I should actually not look at the wave function, I should look at the wave function squared and then make my case. Okay, so that will force me for another few moments of mathematics, but at the end of the day, we'll see that the interpretation remains, but it's important to stress, especially since the whole course I'm telling you, pay attention, a physical quantity can't have an imaginary part. So my explanation at this point was loose. Now I'll do it exactly. Okay. So the probability of finding the particle at point y at time t is a wave function squared. Okay. Happily, I won't need anything here. But I have to write down the Gaussian parts. And this is the only imaginary part in the game. And the fact that we have an imaginary part is not a mistake. It has to be the physics, because as we discussed in one of the previous lectures, a wave function that has only real parts has no momentum. Has no momentum, its position can't change. So if I'm talking here about a Gaussian wave function that moves in the potential, it has to have an imaginary part. Indeed, it has. Okay, so the whole game happens here in the terms of the exponential. Let's write down only these parts. So I have here okay, I wrote it down. The dependence in the Gaussian explicit. Okay, it doesn't look very encouraging. You see from where it comes. Just square here will be 2I omega t, and here minus 2I omega t. I add them together, I guess, cosine 2 omega t. And here I have just one power for the mixed terms, so I get cosinus omega t. Now we pull out 10th grade trigonometry. Okay, just the well-known connection between cosine 2 alpha is cosine minus 2 cosine square alpha plus 1. Okay. Okay. This part of the Gaussian is the part that we know and love. It tells us that the center changes with time as cosinus omega t, which is actually exactly the solution of a classical particle in a harmonic oscillator that change its position as y0 times cosinus of omega t. Okay, so we like this part. What about this part? Come on, you're a physicist. You should be able to tell me what about this part. Does it depend on position?
No.
No. So it's part of the normalization. Normalization started by depending on t, and now I got an additional dependence on t. Great, but it doesn't change the center of the where the center of the Gaussian is positioned. Now I proved that that a Gaussian wave packet, the particle behaves as if its center moves as a classical particle. End of story. Okay, it's a bit earlier than usual, but this is a good place to have a stop before we're moving to three-dimensional positions. So
תקצינו מיום ליום. בוא, תודה. תקצינו מיום ליום, אני כזה רגע כאן.
Okay, so we're moving to the universe which we happen to occupy, a three-dimensional one, and we can have many different types of potentials. 50 years ago, I would say, well, a lot of them could be very difficult to solve. Today I would say many of them are difficult to solve analytically. Feed any decent computer with the Schrödinger equation and whatever potential you feel like, will be able to solve it. That won't stop you from studying a problem, the shape of the potential. But anyway, there's a lot to learn from specific potentials, especially potentials that have angular symmetry, central potentials. Okay, so before that, I'll just say a comment. Basically, any rectangular, square, box type of potential, you know already to solve. Let's say, let's take an infinite box with some which has potential 0 in the middle, infinite everywhere else, you already know to solve. Because you can separate variables to x, y, z, get the solution of an infinite potential for a one-dimensional system, multiply it, no problem. So these types of potentials are easy, and you can solve analytically with no additional problems. Let's say, as I talked about a bit in the previous lecture, if I have a harmonic potential that falls off in the exponent as power of squared in x and y and z direction, we also know how to solve separate variables and solve each one separately. Now we're looking on central potentials. What does it mean, a central potential? We have a potential which in principle depends on our vector, but in this case depends only on the distance from the center. So this is the central potential. And what is special about this potential is that it has a symmetry. You can rotate it in any angle and you'll get the same potential, which leads to angular momentum conservation. And that determines the whole physics of these types of problems. Now, the hydrogen atom is one of these problems. Why? Because the potential depends only on the distance from the nucleus, nothing else, not the angle. So that's why these potentials are so interesting. As usual, I'll assume that your mathematical knowledge is somewhat shaky, so I apologize for those of you who are going to be bored a bit in the next quarter of an hour or half an hour. But for these types of potentials, using x, y, z is the worst thing to do. We will want to move to spherical coordinates, and I'll just remind you what are the properties, how are they defined, what are the properties, and so on. So, okay, these guys are, x, y, and z are defined between minus infinity and infinity. These guys are defined on finite regions. R has no negative component. This is the plus part of the square root. Okay, and to orient ourselves a bit, I'll try to do a 3D plot. Not that I'm very good in it. Okay, so we have some. Take a different color. That's great, but I have here Z, I have here Y, I have here X. So R is easy to comprehend. What I want you to pay attention to is switch these back to X and Y for my convenience. Oh, actually, that's fine. X and Y. Okay, so phi was the total, this divided by this, so it gives you so theta is from the Z, phi is around the plane of XY. This is an important thing to remember. Phi doesn't go beyond pi because if I continue this motion, I can get it just as theta with a minus. Or more exactly, I can rotate phi around to get. Okay. Now, the second part of this table of translation and we can already see that in this definition Z is simple. We exploit this property ad nauseam. Nothing is special about Z. Remember, it's completely symmetric. But if I choose some Z direction, the presentation of Z in this direction is much easier, much simpler. Okay, so this part I hope is no news to anyone.
It's the one.
I've switched it, that is my feeling. Okay, you can always check me, plug it back here and see what you get. Okay, so unit vectors. Is it I didn't switch it here? Could someone check it? Now, the most important thing, you can check everything that I've written here. It's just I'm taking definitions. Okay, and the most useful connection that we'll have here So anyone that it's the first time that he sees it, so he should have seen it before. Check Boas or Arfken, Mathematics for Physicists, a whole chapter which gives step-by-step derivation. At the end of the day, all we really need is this thing. This is bad enough. Why is it bad enough? Because I said we want to solve the Schrödinger equations in spherical coordinates. Let's look on a free particle. If I write it in Cartesian coordinates, we solved it without too much pains. You could separate x, y, z, get the e to the power I, k, x, or y, or z, and life's good. Start treating this beast, it looks daunting, and it's not easy, but in a couple of lectures you'll see that actually you would be able to write down the solution of a free electron in spherical coordinates, and it will even make some sense. Why would I do it at all? I have an easy way to solve it, and it seems to be a very complicated way to solve it. But think about any scattering problem. If I have this electron scattering on some nucleus or something, and if you imagine a wave hitting a small rock and coming out as conserved spheres, describing the sphere part in Cartesian coordinates is a pain. In this language it would be easy. So even for a free electron, and if you're far away from the point of scattering, it's a free electron. It doesn't know anything about it. It's just an initial condition. So even for this problem, there is a physical incentive to know how to write it down in spherical coordinates. So we'll start. We'll see why angular momentum comes out here very naturally. Stop. Forget about the potential, concentrate on the angular momentum, because angular momentum is conserved for any potential. Learn all that we need to know about angular momentum, which there will meet another friend that in first sight is not really connected still. And then return to specific solutions with a specific central potential like the hydrogen. Okay. So we go back to our traditional box of tools, and what do we have there? The usual separation of variables. Always if we have a differential equation that depends on more than one variable, and we can do something to separate variables, or even redefine them and then separate, life is much easier after we do it. So that's the first thing we are trying to do. So I have psi of r It's the first step. I'm trying to separate the r from the theta and phi. Okay. So I have my Schrödinger equation. And when I'm writing here r without a vector, it's only the r component. So I wrote the first term, doesn't depend on theta or phi, therefore it comes before the derivative, but it has a dependence on r. Plus let's use it. Sorry, it's not squishy. Okay. Hopefully I didn't miss anything here. Okay. Let's see what we can do here. Okay, so here I have a term that except for a multiplication by y, no theta and phi dependence. Okay. Here basically I have dependence on R and so first thing I'll do, I'll multiply by R squared, everything. So nothing here, nothing here. R squared here, and R squared here. And as usual, divide by R and Y. So I'm using colors. You figure out, some of you have tablets, so it's easier. Those that have to write, I'm sorry. So here. Oh. Divided by y. Okay, now I have something that's easy to separate to a dependence on R and a dependence on theta and phi. I'll give you a couple of moments to just write it down. Should have screamed on me. I'm messing here with the relative. R, the second
No,
order. It's just sort. I'm putting it incorrectly.
the big R?
Oh, here, of course. First thing, count derivatives. Okay, couldn't have been here. Wouldn't have made the difference. Okay. And of course, R plus R squared V and this is the only part that depend on R. I'll just divide by R squared, multiplied by large value by large R and get okay, this looks like a typical Schrödinger equation up to this term. Potential times the wave function, energy times the wave function here. It's a bit strange. We'll get to it in a moment. Let's write it down in final form. And here I should write some constant, right? Okay, this is definitely some constant. Why I've written it in this way, it's not clear. We could just call it A. Of course, it has a meaning, but at the moment it's obscure. What did I forget here? Forgot this constant, of course. So I should add it here. And remember that here okay, let's write it in 2 steps. This term I just got because of what appears here. So we got here some correction, and what happened to the potential now that I do it correctly? Got another part. The potential, is it still central? Definitely. This is a constant, and 1 over r square is still a central potential. So from that point of view, nothing too drastic happened, but the potential has a correction. Probably no one remembers it from classical mechanics, and probably someone remember? No. But this type of correction appears also in classical mechanics. If you assume a constant angular momentum. So that's one clue that this is connected to angular momentum. The second clue, it depends on the theta and phi part. So we have here 2 equations. One which tells us how the wave function behaves as function of distance from the center. That looks like some kind of a one-dimensional system with a strange potential. At the moment also a strange kinetic energy. And the second part doesn't depend on the potential at all. This is the part that probably in the next lecture will show is angular momentum. Okay, so the remainder of this lecture will go on solving this part. I want to rewrite my function r in a bit different way. Am I allowed? Yes, why not? That's supposed to solve this problem. So I have a term should have screamed on me, r squared. It's good that because I divided by r squared everything. So what I have here is minus h bar squared to n r squared. Good. Let's start just to perform the derivatives. Simple derivative, nothing special here. Just multiplying by r squared. Now I'll perform the derivative. Looks a bit better. We have a simple second derivative. We still have a 1 over r here, but we made some progress. Okay. Now I'll go back and pay attention. R here will become u over r. And r here will become u over r. So 1 over r drops. So I'm ending up with equation 1 this is something that's already very much reminds us a one-dimension potential problem. We have here the kinetic term for you. We have here some potential that's a bit more complicated than my original potential, but still a well-defined potential, and a Schrödinger equation. The only thing that changed here is actually two things. One is the fact that we have an additional term, we have an effective potential. Second, that U is not defined between minus infinity and infinity. It's defined between 0 and infinity. Okay, no problem. So we're solving the Schrödinger equation, which for x, in this case, r smaller than 0, the potential is infinite, because the wave function can't live there. And to the right, for r larger than 0, it's what's given here. Okay. Now, what is the solution? Depends on V. We said we'll ignore V for the moment. So at least we have hope to solve this part. Give me a V, I'll knock my head a bit around the mathematics, but I will be able, hopefully, to solve. What is this part? I said it's angular momentum. I want to prove that it's angular momentum. How do I prove it? Oh, simple. Write down the definition of angular momentum and see what I get. We're doing quantum mechanics, so we need the operator definition. Since we know the operator definition of R, and we know the operator definition of P, and we know how to perform a cross, we're in the game. So, pay attention. L is a vector, so it has 3 components. I write them down explicitly.
the whatever and yeah added some like the some of this.
What I did here is the simplest thing. At the moment I have no physics yet. What did I say? In quantum mechanics, we had classical observables and we associate them with operators. Right? So I'm taking something that could be classical measured, angular momentum. Angular momentum is a vector property. And in classical mechanics, I know how to build it out of other classical measurements. That's R cross P. Okay? So I'm taking that definition, and the only thing I'm saying is, well, what is angular momentum, the operator corresponding to angular momentum in quantum mechanics? I'll take the classical definition of angular momentum and replace the quantum definitions of any variable that appears there with the quantum definitions that I already know, X and P. Yeah. And that's all. I haven't yet associated it with this. Now I'm just writing down the simplest thing that I can think about, which is a definition of an operator that corresponds to angular momentum. I haven't yet shown anything that has a connection with this.
Yeah, I just get where the minus I H bar came from, but
no, H bar came out of the definition of P.
Yeah.
I didn't add it by hand. I just X was R is X unit vector, Y plus Y unit vector plus Z the unit vector, and these are I minus I H bar go to X plus and so on and so forth. So I just and calculated the determinant. That's all. No assumptions, no H bars that were added. Now, we're not working in Cartesian coordinates. We're working in spherical coordinates. in any problems that you'll have to solve, whether in an exam or in real life, if you have to calculate these things, you did it the wrong way. This is ugly, avoid at any cost. This is cute. This is simple, this is cute, you can work with it. So if you come to a question and you have to calculate Lx, stop a moment and say, how can I rotate my axis in order to get it? Yeah, because at the end of the day, there's a symmetry here. So defining your axis in some direction is your prerogative. Don't make life hard on yourself. No point in it.
So we are with so
and well, in physics, perhaps in all of mathematics, symmetry is a key. Dictates how to work, how to go to get to your target is the easiest way. If you insist on doing it without using your symmetry, without taking advantage from the things that you know, don't be surprised that it's hard. It's like trying to enter a room, but you won't use the door. You have to go through the wall. It's a possibility, but why? Last thing for today, and I won't do it in details. You can sit down at home and perform. It's just trigonometry. L squared, which is Lx, just by definition, this thing square is Lx squared, y z. These are defined here. What's written here is L squared of y nothing but dirty trigonometry, nothing, really nothing. And this is wonderful because this is the eigenvector equation of L square operator. And as usual, now we're in our usual game. Finds eigenfunctions, it finds eigenvalues, and
it's for the whole no.
It's part 2 of the separation, variable separation.
What do you mean by part 2?
I gave them names 1 and 2. It was a variable separation, right?
Yeah.
It's not the whole Schrödinger equation. It's one part of it. But it makes sense. If I had x, y, and z and a square, or then I would have the solution for x, the solution for y, the solution of z, multiply it. Here I'll have a solution for r, hopefully once I figure out this thing. I'll have a solution for theta and phi. I'll multiply the two solutions. That's a program. And as usual, there's the mathematical way, go solve this equation. It can be done. There will be a physical way which we will define operators, which will turn out, let's say, very easily to proves that L has to be an integer.